Bonjour tout le monde. It's an honor for me to be the first presenter of this webinar series. Today we are going to talk about expectations and realities of precision agriculture. Before we go into that topic, I would like to introduce my research team that focuses on precision agriculture and sensor systems. As the title says, we are working on development on sensor systems to measure soil and plant characteristics. Also, we work on solutions for geospatial data processing. And finally, the topic of our discussion today. First, let's look into future of precision agriculture or agriculture in general. We understand that automation is getting into area of precision agriculture quite rapidly, and perhaps some of future farmers would look like this. However, as this cartoon shows, we can see that some of traditions of agriculture will remain untouched. For example, in this picture, we can see many sensors, drones, electrodes, but at the same time, we see tractor, farmer, plants, and soil. I would like to start with this short video clip from 1953 movie, which took place in South. And it's a love story, a romance between a young animal science graduate and operator of tractor in a big collective farm. And she is explaining the operator what the farming would look in the future. So one element that film producers thought about that the robots would be a common tool and to use instead of tractors. They left similar implements that were there before. They also recognized importance of telemetry and ability to communicate between equipment and operator wirelessly. They also could foresee how contour maps would look like that we now use for precision agriculture. Also, producers of the movie unmistakably predicted that troubleshooting would be one of responsibilities of operator of that equipment. Like we see that there is a problem, an operator needs to solve this problem, and he is solving this using a speech recognition system, which also quite advanced for that point in time. Today, precision agriculture has become one of vehicles to get into that future. And as recently defined by the International Society of Precision Agriculture is a management strategy that gathers, processes, and analyzes temporal, spatial, and individual data and combines it with other information to support management decisions according to estimated variability for improved resource use, efficiency, productivity, quality, profitability, and sustainability of agricultural production. Basically, we are talking about improvements in terms of economics, in terms of environment, and in terms of social. Also, it should be recognized that precision agriculture is not a magic kit that can solve general production problems, or change dust and rocks into fertile soil, or make it rain more or less, or make poorer equipment do a good job, or change the value of currency. However, precision agriculture can use information to help deal with every specific situation. In order to implement precision agriculture and other elements related to these technologies, we need to apply system approach. And in some cases, this would yield best management practice. In some cases, we might have benefits of variable rate technology. When implementing precision agriculture, it's important to look at soil conservation practices, such as implementation of continuous no-till, improved drainage and land leveling, logistics and monitoring of the use of machinery. Auto guidance, one of the most common practices at the level of RTK. Automatic section control. yield mapping, imagery data, and georeference soil sampling has already become widely accepted practice. Also, we need to take attention in terms of mode of application of agricultural inputs, and definitely looking into variable rate application of lime, variable rate seeding, or management of macronutrients. Based on existing examples of implementation of new technologies around the world, it's important to note that system changes have generated the highest return of investment, while quality control and logistic of operation has been in moderate range of that revenue. And this additional revenue associated with variable rate technologies is quite moderate, but in some cases still can be significant part of benefit of new. Let's take a look at profitability as the difference between additional revenue and required cost related to new technologies. On the plus side, we have potential savings from optimization of agricultural inputs, increase in yield, improvement of yield quality, reduced pressure on environment, which is still difficult to monitorize, and all the records related to agriculture production that can help reveal generic problems and get them fixed. On the negative side, we also need to recognize additional need for capital investment, for time investment, also potential risk, because some of technologies that may be needed this season may not be applicable to the next season because of changing weather pattern, and also insufficient knowledge or knowledge gaps in some set of technologies. In terms of automation, agriculture is one of leading areas. So what we discussed before is going to happen for sure in different production elements and already happening. This graph is taken from the most recent survey conducted by Purdue University related to adoption of precision agriculture in Midwestern United States. We can see that some of technologies already adopted by majority of producers, such as automatic guidance, and some of technologies are still under developing stage. But I'd like to take a look at this spray section control, which hadn't been even included in the original surveys, and now over 60% of producers already use that technology because of its importance to production. And same relates to other technologies available. However, if we are looking at adaptability of variable rate technologies, those numbers are more moderate. We can see that variable rate liming is on the top of well-adapted practices, but there is still some room for improvement. And this is what we are going to discuss more in depth today. In terms of variable rate technologies, it's evident that putting agricultural inputs outside of cropping areas is a bad practice. But sometimes it's just difficult to avoid. And some of precision agriculture tools allow us to do that automatically. Like we can now use relatively large equipment, relatively small fields without too much over-application or under-application. In Canada, we have quite popular idea of foreign nutrient stewardship. In this case, we are looking at all essential elements from use of fertilizer for crop production and how those elements can be. Let's assume that black line represents single transect through agricultural field, and every point identify one and only one most economical rate of that agricultural input. With current recommendations, we have tendency avoiding plant stress, which result in relatively high uniform application rate. Using precision agriculture technology, we have means to reduce that rate by assessing all potential risks related to over-application and under-application. When we look at variable rate technology, we have ability to address local needs at much finer scale, but it's never going to be perfect because we still have some special dependency and uncertainty related to the changes in weather. Therefore, when implementing precision agriculture, we need to consider two levels of control. At the upper level, we have to deal with all the elements related to the system, including defining the range of agricultural inputs suitable for every specific agricultural site. At the fine-tuning level, at the lower level of control, we can implement mechanisms of variable rate technology to match agricultural inputs or agricultural practices to any specific site across an agricultural field. As an example of upper level control can be a decision support system where we can utilize past experience such as existing databases, online resources to define what would be the most optimum application rate for any specific point of space and time. Numeric ag is one of examples where we used historical observations of nitrogen use efficiency for corn production to optimize that rate. Under this framework, we have location, time, and management as key elements that constrain our choice. But rate of application can be viewed as one of elements of optimization. However, other elements could be optimized as well. At the lower level control, we have ability to implement variable rate technology in a complex way, such as using maps, or in a way like auto guidance using AB line. This is an example of controllers that our team built to actually recognize sensor indicator such as field elevation and then change application rate such as speed of the tractor while applying manure according to and match those two characteristics. In this situation, operator can be involved to define that change of application rate within an agricultural field. However, in classical sense of site-specific crop management, it's a complex that involves several different processes and data collection and mining exercises that normally happen off-season. And we create those optimized tasks for the equipment to implement later on. In the next set of slides, we'll go step by step through different elements of agricultural production and see what would be technologies that can be implemented and how. When it comes to soil management, of course, implementation of continuous no-till is one of the most conservative ways to make soil resources sustainable. However, if it's not possible, strip till is a decent solution. In this situation, we have ability to minimize energy spent on agricultural production and agricultural inputs. We also have ability to identify compacted areas and manage those areas independent from the rest of the field. And of course, the most advanced technique is variable depth tillage, which also has been implemented at different level of research and commercialization. In terms of no-till, implemented as a system, it's important to note that direct seeding is just one minor component of the system. We also need to make sure that we pay attention to proper crop residue management, proper crop rotation, proper use of cover crop, implementation of control traffic, which is impossible to do without RTK level auto guidance, and also placement of fertilizer in band. In terms of seeding and planting, the most common strategy is to optimize seed density in response to anticipated water availability through the growing season. This way we can minimize competition between different crops and maximize use of space. However, also some work has been done to optimize planting depth in response to changing climatic conditions so that we had uniform emergence. By default, emergence across agricultural field is not uniform, and in climate like Quebec, it's quite important to catch every sunny day to get our yield. And also a lot of attention has been paid to ability to change hybrid. As one of elements of this would be comparison between different varieties, or we can also match hybrid to growing condition within specific agricultural field. When it comes to site-specific management of water, here in Northeast North America, it's important to pay attention to improved drainage and land leveling. We also have ability to control water table. When it comes to irrigation, one relatively easy technological improvement is optimized scheduling of irrigation. And also variable rate irrigation is of course the most expensive and potentially most rewarding set of technology. In this example, we compared economical impact of different level of variable rate irrigation. And as we can see in this graph, producers pay either way. They don't use technology, so they have lower yield, or they use technology, so then they need to pay for the cost of technology at a given depreciation rate. And in this example, we can see the blue line illustrate increase of the cost of technology when we go from no irrigation to uniform irrigation to speed zone irrigation, and then to controlling different irrigation rate across pivot. And on the other hand, the two gray lower line, they indicate how yield or yield related losses would be imposed on the farmer. And when we combine the two together, we can see that for every site there is a certain level of optimum control that we should implement. In terms of liming, key elements is that yes, we need to add lime when pH is low. It's understood. We also don't need to apply lime if pH is not low, which is quite obvious, but when we do uniform application of lime, we never do it. We actually put in lime everywhere, including locations in the fields that are already alkaline or neutral. And also we need to recognize that soil that has relatively high buffering characteristics will require more lime to change that pH than soil like sand. However, it's important also to recognize that using inaccurate maps is not better than just following that uniform applications that we've always been doing. And as one of examples how to get an accurate map is using on-the-go pH mapping, when we can generate 10-20 measurements per hectare when we drive across an agricultural field. In this example, we used a probabilistic model to look at the value of information that we can get from different types of mapping variability of soil pH. And in this situation, we are looking at net return cost of liming as a result of multiple model inputs, including specific characteristics of the field and different methods used to map soil pH. And we were looking at corn-soybean rotation, where lime is added before corn on the first year and not reviewed until 4 years after. According to this graph, the more accurate maps, they can generate higher expected net return on cost of liming as compared to low accuracy maps. But the difference is relatively moderate. Of course, if you have higher cost of liming or a higher cost of crop, also that difference is getting bigger. But with this exercise that we did, we are looking at a benefit of about $10 to $30 per hectare. In terms of nitrogen management, this can take long time, so I have just key points here. That timing of nitrogen application is quite important. We need to make sure that we apply nitrogen when it's needed, and that's related to those systematic changes that I mentioned before. In terms of site-specific management of nitrogen, we have two schools of thoughts. In one, we can use predictive approach, where based on historical information, based on some of measurement of residual soil, residual nitrate in soil if I'm in dry climate, or using irrigation techniques, we can predict what would be nitrogen availability using like naturally occurring available to the plants, and then we just supplement based on what's needed. However, there is also promising strategy of reactive management of nitrogen, such as side-race nitrogen, when we can measure crop properties in real time and adjust side-race nitrogen application in terms of plant requirement. This graph shows how in-season nitrogen and sensor measurement, which actually indicate predicted yield at any specific point of time, would interact together with respect to potential profit. We can see that for every measurement of sensors, there is one and only one optimum application rate. However, the probability of profit to get lower when we under apply nitrogen or over apply nitrogen is not the same, which is naturally causes many producers to go toward over application, because with current examples like from agronomic research, we don't see such a big yield hurting factors as we can see with under application. When addressing more stable micronutrients such as potassium and phosphorus, it's important to recognize that we can manage them in bands, especially if we have the entire cycle of precision agriculture together with seeding or as a separate field operation. Also, every time we have significant variability in plant available potassium or phosphate in a given agricultural field, it has a lot of relationship with past history of that field management, such as animal production and intensive use of organic fertilizers. Also, it's important to recognize historical yield removal of these nutrients with crop. There is a variety of emerging tools to directly or indirectly measure phosphate and potassium rapidly on site. However, today, grid sampling is still one of the most accepted technique to recognize special variability in these two properties. And I also want to emphasize that using those maps that sometimes don't reflect true spatial variability is not better than following uniform application. In terms of using organic fertilizers, it's a lot of considerations related to environment. So we have ability to avoid environmentally risky zones or reduce rate of organic fertilizer in those zones. It's quite challenging to balance nutrients of organic fertilizer because of heterogeneous nature of this fertilizer. So we can say how much we are going to put in different portions of the field, but this doesn't mean that that's going to be application rate of nutrients that we are going to put in those areas. Also, consideration of different type of products such as using compost also can be helpful. And also one of important elements where precision agriculture can help is minimization of the transportation costs. So we can optimize the route for those applicators, especially if we are working with manure slurry or product like that. Finally, in terms of site-specific weed control, we have a variety of precision agriculture tools that can help improve mechanical control of weeds if it's organic production, etc., and site-specific management of herbicide. Before Roundup and when we deal with sites where there is a significant presence of Roundup-resistant weeds, we have techniques that can just recognize amount of weed at different parts of the field and adjust herbicide management based on that information. We also have ability to change different product of herbicide depending on the species recognized by equipment. And some of herbicides that apply to the soil, the rate might need to be changed depending on organic matter. Soil organic matter, and because soil organic matter is not constant across the field, we also can implement site-specific management of herbicide in that case. This is another relatively old video clip that illustrates relatively straightforward exercise which can help both economical and environmental aspects of precision agriculture. We have a relatively large sprayer going through agricultural field and avoiding applying that chemical in environmentally risky area. And variety of technologies like this have already been available for several years and should be implemented where feasible. And the final message from this presentation is that there is no such case where precision agriculture doesn't work. However, there are many instances where promoted solutions are not appropriate to solve given a set of problems or are not executed correctly. And with this, I'd like to thank everybody for listening and will be happy to answer any questions that you may have. Thank you very much. Merci beaucoup.
Donc, je vais y aller avec la première question qui est pour augmenter la précision de la carte de chaulage ou autre, avez-vous une idée sur le nombre minimum d'échantillons par hectare? Actuellement, on prend peu d'échantillons et les résultats de l'interpolation sont loin de la réalité.
Well, this is a very good question, and it's thank you very much. It's part of what we discussed in presentation. The answer is like general answer. It depends. As one of the most prominent agricultural economists, Viacheslav, who's been working on precision agriculture for about 30 years. And every time somebody asks him about economics of site-specific management, he would always answer it's site-specific. So it's actually quite important to consider how certain property that we are trying to address changes in a given site. We have plenty of examples where it's easy to define acidic and neutral/alkaline parts of the field, and then delineation of the zones to be lined is relatively easy. However, in a stochastic environment, many special dependencies related to pH in this part of the world are around 100 meters long. So at the minimum, if we're doing just systematic sampling, we need to have about 100 meters between samples, and that would mean one sample per hectare. But it still uncovers very little portion of variability that we have in the field. That's why when we develop automatic on-the-go pH mapping system, we were looking for at least 10 or 20 measurements per hectare, so that we get this density of measurement and be able to more accurately delineate those areas. However, I have to emphasize that it's really site dependent, and before we can confirm that special structure is there and the difference is real, I would not recommend do variable rate liming.
Parfait, merci. Donc, j'ai envie de poursuivre dans la même lignée de la question avec la question de monsieur qui demande, nous voyons de nouvelles sondes d'échantillonnage de sol apparaître sur le marché qui donnent une lecture en temps direct de l'analyse du sol. Sont-elles aussi précises que les analyses faites par les différents laboratoires?
Again, thank you for a very good question. There are different methods that, and that could be another presentation when we talk about proximal soil sensing. And those sensors that's been developed or been on the market already for some time can have either direct or indirect measurement principle. And when it comes to chemical properties such as nutrient content, most of sensors that we consider, they use indirect relationships such as optical, spectral measurements of soil in certain conditions, especially right now using artificial intelligence and convolution neural networks. We can generate quite accurate model that can generate results that would be quite comparable to proficiency lab test data that we use as a benchmark to define if measurement is accurate or not accurate. However, I also wanted to emphasize that in our research, we found that even less accurate measurements, if they are done at much bigger density, then the resulting map is more accurate than maps generated using precise measurement, but collected with low density. And that's probably one of the most important elements when it talks to when we are talking about mapping of chemical soil properties. Also, it's important to note that even if we use indirect sensors, different type of high density sensors, we always need to rely and not just on lab measurement, but on specific lab measurement to relate to previous calibration exercise and actually fertilizer recommendation rate that link to a specific type of soil test. Like any soil test is index, and that's something that can be viewed as a relative term. But for your site, for your field, you probably have already established a link to that benchmark facility, such as lab and a specific test that you can rely on to make recommendations. So we can select few points in the field where we do all of this exercise, and then using high density data to fine tune our measurements, like between low and high values.
Parfait, merci. Donc, je tiens à mentionner aux participants qu'on laisse un petit délai là, pour la traduction. C'est pour ça que je laisse ce temps-là. Donc, la prochaine question qui est affichée à l'écran, c'est de quelle manière concrètement pouvons-nous déterminer les besoins en azote d'un champ pour formuler des recommandations et avec quels outils?
Okay, thank you again. It's we have, as I mentioned in presentation, we have this upper level control where we take into consideration weather as well as the characteristics of the site, such as organic matter availability, previous crop, the type of soil management, like precipitation, crop heat index, and so on. And that can give us a ballpark for that specific site in a specific field, what would be optimum application rate. We also have to consider price of grain, as well as cost of fertilizer, whatever form we are trying to apply. But on the field scale, on the fine level, we have ability to use different sensors to either measure organic matter in soil and actually use it in the algorithm. We can use yield history data as one of elements. We can use satellite or drone imagery, or we can measure nitrate on the site. Like there are several tools available commercially where you can identify what the nitrate availability in soil. And finally, we can use sensors that actually measure plant and see what the potential nitrogen stress in the middle of the season if we do side dress application. And all of this technique in one or another region have been shown profitable to implement. Like on site-specific nitrogen management, it's easily can stick about $40 to $50 per hectare cost recovery if it's done properly.
Parfait, merci. Donc, on va rester dans les questions concernant la gestion de l'azote. Selon toi, quelle technologie serait la plus prometteuse pour obtenir des résultats à court et moyen terme pour la gestion de l'azote à taux variable?
Okay, again, let's go back to my previous answer that this is site specific. However, it also relates to the potential for investment. So for example, switching to high clearance vehicles that can do side dress nitrogen, that might be an expensive investment. So going with just a system approach to optimize nitrogen use in a specific field based on decision support systems, that would be an easy task because you don't need to invest in equipment. But then based on those results, based on observation, based on analysis of yield data, one could actually consider investing in another tool that can actually vary application rate on the go, which would be the ultimate goal of this exercise. So it's not the right answer. It's to find what's the sequence of right answers for a specific site, for a specific production area.
Parfait, merci. I will formulate an English question. So we talk about working to help developing countries avoid our mistakes in their development. For example, this can mean soil degradation and pesticide misuse. How do you see precision ag factoring into this in terms of access to the technology? Also, are you worried about the issue for ownership of data by suppliers of technology?
Okay, those are a good set of questions. So first, in terms of soil degradation, as I discussed during presentation on soil management, precision agriculture provides an array of tools that actually can help preserve soil. For example, such technology as strip till without precision agriculture tools would be very difficult to implement. Like people have been talking about this 70, 80 years ago, but it would not be practical without appropriate GPS and so on. Some of producers see precision agriculture tools as a venue to improve their soil management, to actually move toward conservation practice, such as implementation of controlled traffic and things like that. Now, in terms of pesticide use, because now we have ability to apply as needed, we have cases where we can reduce chemical load on environment 70% or more, depending on where we are. And it's not only agriculture, it's all across the board. It's road services, railroads, and everywhere where we use it. Like if you don't need, you don't spray. So that's orchards, like examples all across the board. And in terms of ownership of data, that's quite challenging topic. Because we have two main players on the market. We have banks, insurance companies, and so on that farmers would necessarily want to share data with. And we also have service providers who are eager to help producers. We can clearly see that when we have ability to combine data from multiple producers, we can generate much better recommendations for everybody. But that's actually process of building community, of building trust. And it's not different than social networks. A lot of times people unhappy with what's happening with our data that put on social networks. With all the scandal with Cambridge Analytics and so on that been on news. So in agriculture, we are pretty much in the same scenario. There are some companies that manage very well. They have protocols, they have agreement with producers, and the data is safe and secure. But this can be sensitive to some producers and advisors.
Donc, merci. Donc, nous allons prendre une dernière question, mais sachez, les participants, que ceux qui n'ont pas pu être répondus aujourd'hui pendant la période du webinaire, par faute de temps, celles-ci vont être acheminées à M. Adamchuk afin qu'il réponde par écrit. Donc, n'hésitez pas à formuler vos questions. Donc, je vais y aller avec la dernière question. Pourquoi ne pas utiliser des covariables facilement accessibles, lidar, sentinelle, radar, pour améliorer l'interpolation? Là, peut-être que ça fait référence.
It's part of the system. LiDAR, it's one of the best estimates of topography. The Centennial sees images, and radar, it's also relates to topography, and there is some evidence that we can look at moisture. And that's actually when we talk about, for example, predictive approach to management nitrogen, we have ability to define what's the expected water availability in rain-fed environment. So based on that information, we can adjust our nitrogen application rate accordingly. So those elements of the tools, it's just a matter of cost, and some of those data is relatively inexpensive. Some need to be accessible. It's availability. Sometimes your farm just happened to be in the place that hasn't been covered recently and so on. But certainly, we don't need to stay at proximal sensor level if we have all this data, especially like vegetation history. Centennial is a great tool. Maybe resolution is not great. So for larger fields might work well. For smaller fields, there could be some questions, but it's an evolving process. And combining data from multiple layers and looking what's the most appropriate for given site, that's the best approach that we can take at this point of time. Thank you very much.